Welcome to the next lecture in Geotechnics 254. Today's lecture will be fairly short. In actual fact, it's just basically a very quick recap of flow nets, as well as another example of a flow net in a different scenario. Flow nets are used very widely to determine how water flows underneath physical structures, and if it can cause a problem with drainage problems on the downside of the dam wall, etc. So in this case, the picture that I show here, this is Katsi Dam in Lesotho. The dam wall is a double curved dam wall, so it curves to the front as well as from the bottom to the top. This particular dam wall is almost 1 kilometer in length and it's about 300 meters high. I was very fortunate as a student when we visited the site the first time when I was in my honors year. There was this adit over here, and then in where the dam wall enters the mountain, there were another 4 adits. That was all there was. There was just a river and these small tunnels in the side of the mountain. And we did some investigations. And from then on, every year, I was very fortunate enough to visit the dam as it was constructed from in blocks, and until the day that the water actually started coming out. It took several years, of course, to build. It was built with the original idea was to build a dam from the lava or basalts from Lesotho. But it was very quickly realized that if you excavate the lava and leave it to the atmosphere, it undergoes so-called deuteric alteration, and it started basically turning into mud. So then we had to find the dolerite intrusions in the lava, and you must know they have basically the same composition, so it was very difficult to distinguish between the two. But eventually the dam was built with dolerite. And then you know that as cement cures, it's an exothermic reaction. So on this side of the dam, right outside of the picture, there was a huge construction or a building, which was essentially a slush puppy machine as big as a rugby field. And this slush puppy was pumped through the concrete while it was poured, to keep the temperature below 32 degrees centigrade in order for the concrete not to crack. And then the dam was also supposed to fill up over several years, but just almost before it was finished, there was a huge snowfall, and suddenly there was water rising very rapidly. And to this day, behind this part of the dam wall, there's actually still a crane attached to the wall, which they could not remove in time before the water rose to that level. So it's still there. So sometimes nature throws interesting curveballs. As I said, this lecture is going to be about flow nets again, and very short. Just a recap then. I is the hydraulic gradient, which is delta L over delta H, and V equals K times I, where K is the hydraulic conductivity. Q is the flow or discharge that you will get. U is the pore water pressure, which is often what you want, because if it becomes too high, it can damage your structure. H is the total energy head, and Z the elevation head. The flow net is a graphical solution to the equation presented in the previous slides and also in the previous lecture. Nowadays, finite element methods are used to determine flow underneath structures such as dam walls, but the flow net is a very quick and easy way to determine potential seepage flows. And the flow net depicts the seepage patterns. And on the flow net, you get flow lines and equipotential lines, which you can consider to be families of flow lines and equipotential lines but very importantly, they must obey the mass or the rules. What are the rules? Delta H is constant, and it's H over ND. Q is constant. Q is also, as we well know, KIA, which can be written as K delta H over delta N times delta S. And we say delta N is equals to delta S. Delta N is the distance between two flow lines, where delta S is the distance between two equipotentials, and we choose them to be the same for simplicity. So Q is the flow of water underneath the structure. Capital ND is the total number of equipotential lines, and small letter n, D, is the number of equipotential lines as counted from your chosen side, starting at ND equals 0. NF is the number of flow channels, and capital H is the total difference in head. So if you want to determine the total head at ground surface at datum, we call it AH. Then we set up the boundaries. The equipotential lines is lines of constant head, and we always have an upper and lower flow boundary. You draw the equipotential and flow lines, and remember, the flow lines can never intersect and must follow the flow boundaries, and it cannot intersect the flow boundaries. The flow and equipotential lines intersect each other at 90 degrees, and you form a curvilinear square. In other words, you must be able to draw a circle inside it. So if we take this example, K is given as 8.5 times 10 to the minus 4. So in this case, this dam had another section constructed here, which can be concrete, and sometimes it is a so-called grout curtain, as was done in Katsi Dam case, to inhibit the flow of water underneath the structure. When you draw flow nets, it's always a good idea to draw your flow nets in pencil, because you're probably going to need to rub it out here and there. As you can see, the flow lines follow more or less the structure and becomes more and more flatter as you go further down, and then your equipotential lines are more or less equally spaced, and it will, so they must intersect at 90 degrees, intersect at 90 degrees, intersect at 90 degrees, and that's why if the flow line is doing this, your equipotential line must still intersect it at 90 degrees, and that's why you need to play around when you draw it. So in this case, we say we choose the datum to be at the surface of the water on the downstream side of the dam, 1 meter above ground, and then we start drawing. So our flow boundary is this. The structure itself is the flow boundary and the ground surface, and then this bottom is the other flow boundary. So we say this is line number ND0, ND1, 2, etc., until you get to the last one, which is number 11. So the total number of equipotential lines is 11. H is 5,5 plus minus 1 is equals 4.5, because it is 1 meter below the datum. The datum, remember, it goes, excuse me, the datum is the same on both sides. And in this case, H is 0, because it's 1 meter below the datum at an n value of 0. So capital H is also 4,5 meters, and we want to know what is the flow and the flow rate and the pore water pressure at point A, which is here, and at point B. So Q, we've got from the previous lecture already, K times the total H over the number of flow lines over the number of equipotentials. and that's 8,5 times 10 to the minus 4 times 4,5 over 4 over 11. I go back, so the flow channels 1, 2, 3, and 4. So 4 flow channels and 11 equipotential lines. That's where this comes from. And then you get an answer of 1.39 to the 10 minus 3 cubic meters per second per meter. So every meter length of the dam, this is the flow. So at point A, HA becomes this 0 plus 9,5, 11 over 11 times 4,5 is 3.89. So if you look at this, so 1, 2, 3, 4, 5, 6, 7, 8, 9 and a half. That's where the 9.5 comes from. And you get 3.89 meters. You can also do it from the other way around. 4,5 minus 1,5 over 11 times 4,5 equals 3.89. Remember in the previous lecture I said if you count from left to right, then the equation becomes a minus. So at the flow, the pore water pressure at B is the unit weight of water times the height at B minus the Z at B, and H is U over unit weight of water plus Z. So HB becomes this. It's 0.9 meters from 0, 0.9 distance from before it gets to NB1. So it gets 0.37 meters. So UB becomes 10 times 0.37 minus 2, and that gives you 23.7 kilonewton meters per square. That is the pore water pressure at B. I really advise you to play around with these examples. Try and redraw them for yourself. Look at the examples given in the handbook, and please look at the video by Dr. Franke that I made available. He has a very nice way of explaining this further or in a different way. Flow nets are important, and this is an exam tip. You will get one. So be prepared. Thank you very much. Until next time.